everybody. Set my timer. I'm trying to get 20 minutes into a 10-minute presentation. Well, great. Here it is. Happy to be here to present today. My company, Brightcore, provides a lot of ESG solutions. My group is the Renewable Heating and Cooling Group, but mostly what we're providing to the marketplace is turnkey geothermal solutions. So we can provide everything from the feasibility stage through construction, operation, with even options for financing, long-term PPA style financing. But here we're going to focus on our urban geo offering. Next, I control this myself. Does anyone know which green button? Thanks. So first, a little bit about geothermal systems. These days, it's most common that people install closed-loop geothermal systems, which are pretty much big ground heat exchangers that are exchanging energy from the surrounding geology. This graphic here kind of illustrates how these systems operate. We like to say air source systems are really good, but ground source is better. This illustrates that during peak heating conditions in the wintertime, air source systems are getting their heat from a 25-degree source. The ground is generally about 30 degrees warmer than that. And in the summertime, air source heat pumps are rejecting heat to warm conditions outside, about 85 degrees in the summer. And conversely, well, in the wintertime, the ground is much cooler, so it's easier to dissipate heat to the ground. So there's a large mechanical advantage. So what we're bringing to the marketplace, so it's pretty innovative, is ways to install and operate geothermal systems either for new construction or in the built environment. So the core of our innovation that we, I guess, use as a basis to describe what we're doing is a specialized drilling tool called a water hammer. This water hammer differs from what technology is generally used to install geothermal in that water is used instead of air to drive these hammers, and they use much less energy to do that. They create much less noise, much less vibration. They don't create any dust, and this allows for the installation of the systems to be done on construction sites in a much less invasive way or in retrofits. This picture actually is from an installation that our partners did in Sweden that retrofitted a building with 80 boreholes in the basement of a building. And here's a computer graphic of that design. And you may notice that this graphic is a bunch of lines, and they're angled as they extend downward. So what this represents is the surface area inside of a building where this system was installed. It was about a 14,000 square foot open area in a basement, a parking garage, where they drill downward directly vertically and also at inclined angles. This allows to capture a lot more thermal mass than could be considered before with conventional drilling technologies. So they went down from grade down to about 650 feet, and they stayed on the property. The drilling is very accurate, and we can survey it. It's generally as accurate as 1% to 2% from deviating from where our terminating points are designed to be. But today we're talking about thermal energy storage. Another inherent quality of ground source systems is their ability to, I guess, provide, I like what Paul said, thermal inertia, or kind of act as a capacitor that can buffer the loads of a building. And in a sense, this does qualify as thermal energy storage if you're using these systems to offset upcoming loads. We're really excited to have been a recipient from a grant, a generous grant from NYSERDA. The Next Gen HVAC pond had a thermal energy storage component last year, and we were picked. I think there were about 80 applicants, so we were really fortunate to get selected. This building in the graphic is the Beresford Building on Central Park West, and we're doing a geothermal retrofit inside of this building. There's a lot of talk about how systems and buildings need to be reconfigured to be able to electrify. This type of configuration is utilizing a heat recovery chiller. And this heat recovery chiller is providing heated and chilled water to fan coil units throughout the building's lobbies and offices and some other accessory spaces. What's different is what's on the load side, on the left-hand side. So on the left-hand side, you'll see geothermal wells that are circled on the lower left-hand corner of this, and an air source heat pump that's on the upper side of the graphic. And the way this system can work, the way the system is designed to work is that it's going to operate as a standard ground source system for the majority of the year. But during peak cooling conditions, it helps serve this cooling dominant area by storing up or preconditioning the loops during overnight periods. And this will provide, we're modeling an 18% reduction in energy during peak cooling. It also provides all the benefits of ground source for a coefficient of performance, just very high COPs during heating. And what I like to illustrate is that during heating, this system is about 64% more efficient than an air source solution. So it's quite dramatic. The COP for a system like this hovers around 4 during the coldest days of the year. And that's it. Are we taking questions or just presenting? I don't know. A little bit of time.